Hi, this is Chapter 2 of our Chem 7, and so I'm going to talk about the atom and the periodic table in this lecture. So an atom is the smallest particle of an element that still has properties of that element. So you can cut a big piece of gold down to smaller and smaller sizes, and each one of those pieces will act like gold, and even when you get down to the atom level, it will act like gold. So the modern atomic theory says that every element consists of little tiny particles called atoms, and each atom acts just like the element, even like a large portion of atoms. They all act the same. And when you get down to the smallest particle, it's called an atom, and that atom still acts like the element itself. All atoms of an element are the same, except sometimes they have different masses, but they all act the same way. Atoms form compounds when two or more elements combine together, and in any compound, the ratio of the different atoms is always the same. For example, H2O, water, is always two hydrogens hooked up to one oxygen. And when chemical reactions happen, atoms are never created or destroyed, they're just rearranged into different compounds. Here's some symbols, and remember we talked about this a little bit before. Each element has a particular symbol. Sometimes they make sense to us, and sometimes they don't, because some were using names from way back in the day, the Greek and Latin times. So remember, some elements just have one letter, and it's a capital, and some elements have two letters, and the first letter is always capital, and the second letter is a lowercase letter. You won't have to memorize these, but you'll just get familiar with them when we use the periodic table. So each atom has parts, and the center of the atom is called the nucleus, and it's got two different parts inside that nucleus. There's protons, which have a positive charge, and neutrons, which are neutral or no charge. So the letter of the name says that protons are positive and neutrons are neutral. And that's in the center of the atom, and that's where most of the mass of the atom occurs. And then we also have electrons that are moving around on the outside of the atom, and electrons give an atom its particular reactivity with other atoms. So electrons are really important. When you look at the periodic table, it's got a lot of information, and we need to know how to read the periodic table. You don't have to memorize these things. You just need to know how to read the periodic table. So for example, the number at the top of the little square for an element is its atomic number. The atomic number is the number of protons that are in that atom which reside in the nucleus. The symbol is in the center, so hydrogen is represented by the letter H, and it's got one proton, and its mass is 1.008. It has a mass of 1, about 1. Copper, on the other hand, has 29 protons in the nucleus and has an average mass of 63.55. So these atoms, on average, don't have a whole number for their mass, because we have some of the atoms have different masses. So we average all the masses and give that as the mass of an atom, of the average of all the atoms. Mass number is equal to the protons and the neutrons in an atom. And sometimes we write it like this, especially when we're talking about nuclear reactions. The mass number's on top, and remember, mass is protons plus neutrons. And then the number on the bottom, so this is mass number on top, protons plus neutrons, and the number on the bottom is the number of protons, the atomic number. So isotopes, you're seeing on this slide two different isotopes. the protons are always 6 in carbon. You see a 6 there and a 6 there. That's the atomic number, and that's the number of protons that carbon has, and that does not change. The thing that changes is sometimes carbon can have different numbers of neutrons, and that makes the mass different. So for carbon-12, it has a mass of 12, and for carbon-14, it has a mass of 14. So these are called isotopes. Each carbon atom still acts like a carbon. It just has different. Have a different weight. So we're going to do these practice problems in class. So I'll do those with you guys in class. So, like I was saying, the atomic mass is an average of all the different atoms that we know of. And, for example, like if we're sitting in class, each one of us has a different mass. We have a different weight if we got on the scale. And if we wanted to know the average mass of the class, we could just take all the weight together and divide by the number of people in our class. Well, that's what they do with atoms. They have atoms with different weights. They weigh them all, and then they divide by the number of atoms that they have, and that's how they figure out the average mass, because we have different isotopes that have different masses, just like each student in our class has a different mass. The electrons are really important in an atom, and they tell us the reactivity of that atom with other elements. And so we can have electrons in an atom, and we can have some that reside really close to the nucleus, and some electrons that reside farther and farther away. So the bigger the atom, the farther down on the periodic table it is, the more electrons it has, and then the more shells it has. So electrons are important for reactivity. The periodic table is arranged really, really logically, which is nice. So all the elements that are in this group right here have one electron in their outermost shell. And that means that they all react the same way. So this is a group or family of elements, and they react very similarly because they each have one electron on the outside. The electrons, especially on the last shell, tell us how that atom wants to react with other atoms. So group 1 atoms have only one electron in their outer shell, and that makes them react a certain way. Elements in group 2 have 2 electrons in their outer shell, and that makes them react a different way. So as you go across, each atom has a different number of electrons in its outermost shell, and those are called the valence electrons. When we have different atoms, they can react differently when they interact with electromagnetic waves. So when you look at a copper atom, it looks different than if you look at a gold atom or a carbon atom, which looks like the graphite in your pencil. So all those interact differently with electromagnetic waves, just because of how the electrons are arranged in the atom. So when a light hits an atom, it interacts with the electrons in those different shells I was showing you, and gives off different colors. So if we burn an atom in a Bunsen burner, and we look at the color that it gives off when it's burned, that's called the emission spectrum. And so for hydrogen, it gives off these 5 lines, and when we average those together, it gives us a particular color. So every atom, when it's burned in a Bunsen burner, gives a different emission spectrum, and when you average all those colors together, it gives a different color. So this happens all the time. So different energy can hit an electron and make it bounce 2 different shells. For example, this one here, I have electron normally likes to stay in this shell, in this location near the nucleus. If I bombard it with energy, it can jump into an outermost shell and then come back down and relax and give off that energy. So you see that all the time when you have anything that's glow in the dark. You put the glow in the dark object in the sun. The sun's energy hits it, it makes the electrons jump into an outer shell, and then at nighttime when you see that glow in the dark object, that is when this electron is coming back down and giving off the light to your eyeballs. So that's how we can make electrons jump around inside of an atom. The more these electrons jump, the farther they jump, the different colors that you get. So here's a periodic table. And you notice it's arranged logically with columns and rows. So we have columns, those are called families or groups. And we have rows, and these are called periods. So that's why we call it the periodic table. This whole period has a unique pattern. And each of the periods reacts similarly as you go across. So we need to know that the blue guys are metals, and they react a certain way. This group right here are called the metalloids, and those are the things you find in your cell phone. And they act a certain way. And then these are nonmetals, and they react a certain way. So it would be good if you knew the groups. Alkaline metals are group 1, alkaline earth metals are group 2, halogens are group 7A. So we'll be using those, and noble gases are group 8A. We'll do practice problems in class. So each sublevel of an atom has different electrons that live in those particular orbital shells. And I just want you to know that as you get farther and farther from the nucleus, the atom can hold more and more electrons. So the way electrons are arranged in an atom depend on the distance from the nucleus, and the farther you get out, the more electrons you can hold. So for example, when we're really close to the center of the atom, 1s, we can only hold 2 electrons. And also, when we get to the 2s, which is a little bit farther out, we can only hold 2. But as we get farther and farther out, we can hold more and more electrons. So we'll do practice problems in class. And these electrons live in a particular shape. They move around in a particular shape. So S's are always spheres. Electrons are inside those shapes, and they're moving around, but they stay within that shape. And p orbitals have a dumbbell shape, and the electrons are inside that shape, moving around, but staying within that boundary. And all of these come together into, all these shells come together and make one overall shape for the atom. We'll do practice problems in class. We're going to talk about radioactivity next. So the overall thing to know about radioactive decay is you have a parent nucleus in an atom that's not very stable, and it wants to break down into a more stable product. So it will have an unstable parent react and turn into a daughter nucleus that's more stable, and give off a nuclear particle. So there's different nuclear particles. An alpha has this little symbol, and it's the same thing as a helium nucleus. And a beta is ejecting an electron. So if you have nuclear alpha decay, then this would be a helium nucleus. If you had beta decay, this would be an electron. And we write them like this. So alpha has a mass of 4 and 2 protons. Beta is just 1 electron. And gammas are just pure energy. So you can see this is alpha decay. You have a parent that's unstable. It's got a mass of 210 and 84 protons. It gives off this particle, which is an alpha particle, and when it does, it reduces its overall numbers by these. So 210 minus 4 is 206, and 84 minus 2 is 82. So polonium-210, when it decays, becomes lead. And it's much more stable this way, and it likes to stay that way. Beta particles in beta decay is just an electron that's ejected. So we have carbon-14. It had 14 mass and 6 protons. And when it loses this electron, it changes its protons to 7. And it becomes nitrogen. And gamma decay takes an unstable nucleus, loses some energy, and then it becomes stable. We'll be doing half-life problems in class. And half-life is how long does it take a particular atom to lose half of its mass and change into another element. So how long does it take for half of the original element to change into something else through those different decays that we just showed you? So it's time, it's the amount of time it takes for that to happen, for half of the original to be gone and changed into something else. We'll do practice problems in class. So the problem with radioactive decay is these particles can have a lot of energy, and then they can go into the body and damage tissue or damage DNA. So that's called ionizing radiation, where you're actually changing elements in the body into ionized elements, and those things can hurt muscle tissue and bone tissue. We measure different amounts of radiation by a Geiger counter. And each one of these types of radioactive decay has a different amount of energy. So alpha is is the lowest amount of energy, and so you can actually stop an alpha particle with paper. When you get to beta decay, it's going to take lead to stop it. That's why when you go to the dentist, you wear a lead apron over your front of you, so you don't get too much exposure to your reproductive organs and other organs. So lead stops that. And gamma is the most energetic, and it takes a lot of lead to stop it from getting to your body. So nuclear fission is when one particular unstable atom breaks into pieces. So that's fission, when you have one thing here and a lot of particles here. So fission starts with a neutron. You take a neutron and you speed it up and you make it hit into an atom, and that atom breaks off neutrons, and then they start hitting other atoms, and it's a chain reaction. So it gets bigger and bigger and bigger. Fusion is the exact opposite. It's where you take two atoms and you bond them together and you fuse them, and they turn into a larger atom, and you get energy out of this. So this is what's happening in the sun. We have hydrogen gases being heated up and fused together in nuclear fusion. And that's where the sun's getting all its energy to send to us, by a huge fusion reaction that's happening in the sun. We can get nuclear energy from nuclear reactors. And the problem with these is, where are we going to store the radioactive waste when we're done with it? So that's where people are having trouble saying, why should we use nuclear power or not? Another use for radiation is for taking food and irradiating it to kill off any bacteria, and then it can have a longer shelf life. And that's the end of our show for today. So I will talk to you and review this in class. So this is an overview, a quick take on Chapter 2 information, and we'll talk more in class, and we'll do the practice problems in class. So hopefully this will help you understand the second chapter of this class. Thank you so much. Bye now.